Hi, Dr. Bones here with my associate Skelly Skeleton. We're talking about hydrogen. Hydrogen has one proton and one electron. If you wanted to form a hydrogen molecule, H2, you need to bring two hydrogen atoms together. There is an interatomic attraction because there is a plus charge and a minus charge attracting, and a plus charge and a minus charge attracting, meaning that two atoms have these available. And you have repulsion with the electrons and also the plus charged protons. Now, if you've ever seen a parabola, it kind of goes like this. Well, you can do what's called a potential energy diagram, that you can actually think about the potential energy of these two atoms coming together. At the bottom of the well, meaning at the bottom of the parabola, pretty much a harmonic oscillator. It's going to be in its equilibrium position. And you can pretty much take the harmonic oscillator and the parabola as the ideal condition for the vibrating molecule, as opposed to other points in space, meaning when it's stretched far apart or too close together. So if I've got a couple of atoms, here we'll just take these two here, all right? Got a couple of atoms, here we've got two hydrogen atoms. If they're far apart on the potential energy diagram, here we're going to go like this and swoop up. When they're close together, repulsion, so high in energy. And then as it sweeps down, they're going to be vibrating at the bottom of the potential well in equilibrium. And as you sweep the other way, they start to drift apart till finally they're infinitely far apart. I showed this diagram in another segment. So here they're too close together. They're trying to push apart. Here they're at the equilibrium position. They are vibrating in equilibria. And then as you start to go further apart, they start to do what? Become hydrogen atoms again, all right? So what would happen with helium? We said that hydrogen has one electron in an s orbital. What if you took helium, which has two electrons in an s orbital? Well, the problem with the s orbital is that you've got two electrons wanting to be in the s orbital, but you can only put two electrons in the s orbital. And what happens is, sort of like a pair of shoes. You can only put the two shoes or a pair of shoes in the shoe box. And interestingly, there's a thing called spin with the electrons, kind of a mathematical construct called the spin. What happens when you put shoes in a shoe box? You don't put them in this way. You put one shoe up and one shoe down. Well, in electronic structure, we talk about the electron having a spin up or a spin down. So in the s orbital, we can have one electron spin up and one electron spin down, and you can pair them in the orbital. And that's what happens with helium. Helium says, a helium atom, I've got two protons, I've got two electrons, all right? So you've got a neutral charge, and you've got one spin up, one spin down. The orbital is closed. So when another helium atom wants to come by, says, I would like to bond with you, the first helium says, I've got my pair of shoes, all right? My two electrons, closed shell, all right? I don't want to hook up with another helium atom. And they don't, okay? So you're not going to see a helium dimer or molecule. What happens at really low temperature, you can get these to kind of condense with each other, but you really wouldn't call it the helium molecule like you would call it the hydrogen molecule, okay? So that's a condensation effect. So helium-2, not going to happen because each helium atom's got a pair of electrons, right? One spin up and one spin down. And that's where we talk about these gases as the noble gases. We have closed shells in the noble gases. And as you go a little bit further down the table, you can start to see some reactivity with these atoms. But as you proceed back toward helium, you're going to see virtually no activity with helium. Helium not wanting to react with helium or other noble gases, all right? under normal conditions. All right. So, if this is the case, what happens with other elements? Well, with other elements, you may have electrons in the so-called outer or valence shell that are unpaired, and you can bring various atoms together to form molecules. If I took, say, one of the chlorine atoms in the halogen group and paired it with a hydrogen atom, I could form a hydrogen chloride molecule. All right, so I could form the dumbbell shape or the hydrogen chloride molecule, and between the two atoms you would have an interatomic bond, and this bond would be vibrating. So you'd have a vibrational motion of the two atoms vibrating back and forth, back and forth. Okay, so energy can be stored in the vibrational motion, all right? Whereas with helium, you're not going to have the dumbbell. You're not going to have a diatomic molecule. So you have to bring together atoms that want to form molecules. So you need to have open orbitals, okay? All right. Now, what about these orbitals? We mentioned the s orbital was a spherical orbital, all right? And you have various size s orbitals, 1s, 2s, 3s, 4s, 5s, meaning the more electrons you have, you got to put them somewhere. We put them in s and p and d and f and so on, orbitals, okay? The s orbital spherical, the p orbital kind of looks like a figure 8, all right? So the p orbital, and they can be oriented along the Cartesian axes, the x and y and z, all right, in space. Again, this is a geometric construction that's helpful to chemists and physicists, all right? So we like to have geometric models so that we can kind of think about the atomic world. We'll never really know exactly what's going on there, all right? But we try to imagine what's going on there. And so geometry is useful in helping us understand this. And the d orbitals kind of look like four-leaf clovers, all right? So you've got these lobes that can be oriented in space, all right? So you can put it in one plane and then to another plane and then another plane and so on and bring them all together, all right? So let's talk a little bit more about the sizes of atoms. Say this is the hydrogen atom. It's got a proton and an electron, really small. Got a moderate-sized atom. Say, for example, chlorine. We go to the periodic table, we see atomic number 17. 17 protons, 17 electrons. Well, guess what? You want a really big atom? They're available, okay? So, for example, we might say we've got the lead atom with 82 protons. Well, 82 electrons. So you can imagine these various structures, right, from very small to medium to very large, because the electronic structure is going to be out in space, further and further out in space. The bigger, the more protons, the more electrons, the bigger the atom. All right. In the next segment, I'm going to be talking about some interesting molecules that are in the atmosphere. People have been talking about CO2 as a global warming gas. And of course, water is also a global warming gas. Most people don't talk about it. So we're going to talk about the molecular structure in the next segment. All right? I'll see you then. Take care. Bye for now.